So yeah, as Gary was talking about, I saw a few emails going back and forth, people talking about potential meeting ideas, and I saw several of the suggestions were on phase, and I said, hey, I just did a PhD dissertation on phase. Maybe I can talk a little bit about this. So I'll kind of go through some basics. Just talk about what is phase, make sure that we're all on the same page. There's a lot of confusion out there, as Gary mentioned. Then I'll talk about a few useful applications of phase, show you, play some audio demos of some stuff I'm sure you guys have heard before, and hopefully a few things you haven't. And then I'll talk about the difference between phase delay and group delay, because I think that is something that is even less understood than phase itself. And then I'll talk about some psychoacoustics, some of the early experiments starting in the 40s and 50s, going up through the 70s, and then some more recent stuff that's happened in the past decade or so. So, let's get some basics. So, I think most of the electrical engineers, at least in the audience, have seen one of these before. So, if we have a wheel and we spin around the wheel on the left, and then you look at that projection over to the right here, you see that you get a sinusoidal wave. Obviously, the amplitude is pretty self-explanatory, so how far away you are, say from the center of the circle here, will determine the amplitude of the wave. How fast you're spinning around the circle is the frequency, but then where you are on the circle at any specific moment in time is the phase. So really you can think of the phase as being the position or the time. Or even if you know the frequency, you can just figure out where you are based on counting the time into starting that sinusoidal wave, assuming you know where it started. So there's, if you're talking about a phase shift, it's basically just shifting forward or backwards in time. So you take say the red wave and you shift it to the right, you get the blue wave. Or you could actually see this as being shifted to the left far enough that it wrapped back around. And that complicates things even further. But the idea there is you can measure some difference between these two waves, and that will be what we'll call the phase shift. So if we wanted to introduce that phase shift, there's several things we could do. We could just start at a different point. Instead of starting at the far right side of the circle, we could say start at the top or the left or the bottom or anywhere in between, and that would give us a different phase at each point in time. So say if you're synthesizing a signal, you could do something like that. Of course, if you just hit play, sooner or later, that'll actually change the phase from where it was to slightly later in time. Of course, if you're actually playing a sound, you could also just move the loudspeaker. If you move the loudspeaker toward the person or away from the person, or if you're using a measurement microphone towards or further away from the microphone, then you're going to be changing the phase there as well. And of course, you can electronically filter the signal. And I use filters in quotation marks because I consider a delay a type of filter. An all-pass filter, even though you're getting the same frequencies, is still filtering the signal, but you're delaying the signal in some way. And of course, I think most of us have seen this kind of thing. If you take two sine waves, the red and the green in the background here, and you shift them, this is actually just keeping the red constant and changing the frequency of the green, but the phase interacts, so you get this constructive and destructive interference, and so you see the blue wave changing here. And we'll see this pop up more and more throughout this talk. You see this beating pattern, and that's definitely one of the ways you can identify that there's some phase interaction going on. So, some useful applications. So these are things that I think a lot of us have seen before, but may not have really recognized how important phase is in a lot of these. So, simple comb filter. So you take the signal, you delay it, and then you add the original plus the delayed version. I think this one is some music. So every 2 seconds, I think, in there I change to a different comb filter, different amount of delay. So hopefully you heard a little bit of something going on in there. Maybe not easy to explain, but there's comb filtering going on there where you delay the signal relative to itself, and then at the frequencies which happen to line up correctly, those cancel each other out. So you get dips in the frequency response. And then some other fun things, just some sound effects like, I think this one's a flange. So that's basically doing a very similar thing where you just delay the signal and add it back to itself. That's the modern way to do it. The old way was just put your finger on the reel. This is a phaser. So it's doing a very similar thing, just adding a delay to the signal, and then adding the original plus the delayed version back to itself. And actually what's happening there is the delay is increasing and decreasing, kind of in a sinusoidal fashion. And the phaser uses the all-pass filter that I referred to, which is basically just delaying different frequencies by different amounts. So it's a little more fancy. But definitely these are things where phase comes into play big time, and very audible. And of course you can just do a general digital filter. Here's just showing an FIR filter. Basically you just delay the signal a bunch of times. You can add some amplification on each delay element here, add them all up, and you can get some modified version. So you can think of this as one application is to model reflections off the walls. So as I'm talking, there will be a reflection going off this wall to your ear, from that wall to your ear, and all over the place. And that's basically what's happening here, and that's how a convolution reverb works. So you might end up with a frequency response over the room that looks kind of like this, where you see kind of a comb filtering effect, where you see there are nulls in the room. So, you know, this one here, you know, was a very low frequency in a large room. But as you go higher and higher in frequency, you get smaller and smaller nulls. Let's see, what was this? I believe this was a demo of just reverb. I'm sure you guys have all heard of reverb. So the basic idea there is this also is just phase. Lots of phase shift, so it's very audible, but along the same lines. It's just time delaying something and then looking at the effects of that. So, and of course this general filter can be designed, you know, lots of people spend lots of time designing these filters to be all kinds of responses. Another one, you know, for everybody that is familiar with noise canceling headphones, this is basically what they do. You have some signal coming into the headphones, you have some polarity inverted version of that, which is trying to cancel out the noise so you hear less of the noise. And that's very dependent on the phase. As I'm sure anybody who's actually worked on one of these, the phase is very important if you're trying to accurately cancel the sound. So yeah, we can get into that if anybody wants to talk more about that. This is kind of a side note, but I thought it was important to make a distinction between phase delay and group delay. So I just took a simple filter. Here I'm just designing a low-pass filter, cutting off at about 4 kilohertz, just as an example, but this happens all the time. With any filter, you get some phase delay and group delay. So here's the phase response of this filter. We can see that it starts rolling off at fairly low frequencies, and then it gets really steep right at that 4 kilohertz area where the frequency response started rolling off. And then it gets shallow again. And then we can also calculate the phase delay and the group delay based on this phase response. So the phase delay is just basically the phase at each frequency. So if you were to mathematically calculate it, it's the negative of the phase divided by the frequency at which you're looking at the phase. And then the group delay is actually just the negative derivative of this phase. So basically the slope of this phase response. And so both of these will give you some delay in seconds. So you can count that. And if you were to actually plot the delay as a function of frequency, it would look something like this, where the phase delay is in the black there, and the group delay is in the blue. And you can see that they're different, first of all. The group delay peaks up right around 4 kilohertz there at nearly a millisecond of group delay. But the phase delay peaks a little bit later, and you're only getting about half a millisecond of delay there. So just to point out that there's a big difference there. And then if we were actually to pass an audio signal through this filter, this would be what it looks like. So the top here is the input, and the bottom is the output. So this is just a 4 kilohertz tone modulated at 500 hertz. So you can kind of see the fine structure, if you will, the 4 kilohertz tone, but also the modulations. So the envelope of the signal is what you're seeing as the big modulations there. So if you were to actually look at the time difference between the top and the bottom, the first thing you notice is that the top starts at 1 millisecond, the bottom starts at about 1.5 milliseconds. So you have a delay of about half a millisecond, which is what we saw as the phase delay. So the phase delay is actually representing the delay of the signal, really. But then if you were to actually look at the envelope of the signal, we'll say the envelope peaks around 1, 3, 5, 7, 9 milliseconds, whereas the envelope on the bottom peaks closer to 2, 4, 6, 8, maybe a little bit less than that. But actually, if you look at the group delay, it was a little bit less than a second. And we're seeing a little bit less than a second of delay on the envelope of the signal. So the phase delay tells us about the actual delay of the signal, of this 4 kilohertz signal. But then the group delay is telling us something about how delayed the envelope of this signal is. So they're going to be delayed by slightly different amounts. And of course, it depends on the filter. This happens to be a very steep filter, so there's a bigger difference. But that was intentional to show you how big of a difference you can get. So in other words, phase delay is the delay for a specific frequency. And then group delay, you can think of it as the delay of the envelope, but then that gets a little tricky. So you could think of it, if the slope of the phase is approximately linear, then usually you can think of the group delay as the delay of the envelope. But if it's not approximately linear, then that kind of falls apart. And one example that really caught me was when I first discovered that the group delay can actually be negative. So if the slope of the phase is negative and then it turns positive, that means the group delay is positive and then suddenly it goes negative. And negative group delay, meaning that the sound comes out before it goes in, does not actually happen. Time delay does not exist, or time travel does not exist. So interpreting group delay as delay of the signal is not really always accurate. So let's get into some psychoacoustics. The easiest one is when you think about interval time differences. Say if I'm to your left and I'm talking to you, the sound reaches your left ear before your right ear. That's a phase difference between the signal at your two ears, and you detect that as being a cue to what direction the sound is coming from. Also, when you're measuring critical bands. So the critical band idea is just that your ear analyzes sounds in specific frequency regions. And one of the early ways that critical bands were measured was by looking at phase differences. So if you compare an amplitude modulated signal to a frequency modulated signal, here on the left at the top kind of shows a simplified spectrum of an amplitude modulated signal. You get the carrier with the center frequency here, and then some side lobes to the side. And then with a frequency modulated signal, if you assume that it's only modulate a little bit, so you only get the two sidebands. One of the sidebands is going to be polarity inverted from the other, so 180 degrees out of phase from the other. I'll just leave that as is. But the idea here is the difference between this AM signal and this FM signal is just the phase. And you can actually hear the difference at when these frequencies are close together. So the modulation frequency is relatively low. These spectral components come close together, and you can hear the difference. So the plot here on the right shows just kind of a schematic of what it would look like if you looked at, on the left is just a little bit of modulation. You're pretty sensitive to the AM modulations. In other words, you don't have to get a whole lot of modulation depth to detect those. And then if you keep modulating further than that, then you can start detecting the FM signals. But then once you start modulating faster and faster, these frequencies spread out from each other, and once it exceeds its critical band, you can't tell the difference anymore between the AM and the FM. And that's just one of, I think, 4 or 5 different ways that people have measured critical bands. And so it tells you that within a critical band, within some narrow frequency range, you can hear these differences between the phase. But then once you get outside this frequency range, then you can't hear these phase differences anymore. So that'll be an important point to remember, that phase sensitivity is you have to have phase differences within a pretty narrow frequency region. But once you say if you wanted to test the phase at 100 hertz versus 10 kilohertz, that's going to be practically impossible. So. Just a quick note on detecting phase differences. There's a lot of research on how well people are able to detect phase differences just by themselves. You just take, a lot of these experiments have just taken, say, 3 tones, just to make it pretty simple, and change the phase of one of the tones. And pretty much the results are, yes, you can detect it. And it really depends on the amplitude of those tones and the relative frequencies, and then how much phase difference there are between those. But the main story is, with these very specific test conditions, you can detect the phases. And they usually manifest themselves as either a modulated envelope, so as we saw before, where you see the envelope of the signal is modulated as the, say, 2 signals interact. Or often you also get frequency modulation. So the frequencies are modulating back and forth when the phase of 2 signals interact. I think I had a slide in here that I took out, just emphasizing that any complex signal, whether it be speech or music or pretty much anything, is composed, you can think of it as being composed of just a bunch of these tones. So a lot of these perceptual experiments are based on very small set, just a few tones. And so as you add more and more tones to get into, say, music, it complicates things a bit more, of course, but the same principles apply. And we'll see some of that. Another experiment that was done in the 70s was to take a harmonic complex and shift just one of the tones in that harmonic complex. And they found that if you shift one of those by at least 30 degrees, then you can hear that. So this example here is just a harmonic tone complex, and I think I've taken several of the tones in that complex, shifting them out of phase, then back in, then out, and then back in. So you can hear what that sounds like. So definitely a timbral change when you affect the phase of those. Binaural pitch, anybody who wants to come up afterwards and listen to this one. This one is that noise I played. You have to listen to this one through headphones, but basically it's a broadband noise, and you just delay a narrow frequency region in one of the ears and not the other ear. Some guy posted this online. He hid a song in the noise. So you can only hear it if you're listening through headphones, but it's a fun one, so feel free to come up afterwards. All right, some of the most recent stuff. So Michael Hines in 2001, he built a computer model. This is based on how the auditory nerve represents sounds. And he was trying to figure out how can we model how people perceive loudness. So obviously if you increase the intensity of a sound, it'll sound louder, but it's not necessarily a linear relationship. So he wanted to see if he could predict how the brain essentially decodes this information. And so basically the idea is that as you increase the level, the firing rate of these neurons should increase And he figured, all right, you just count the number of times these neurons fire, and that'll tell you how loud it is. But it wasn't that simple. That didn't really work well at all. But then what he did is he added in some information about the timing of when these neurons are firing. And what he did is basically look at when adjacent neurons are firing. So let's say you have a neuron connected in the cochlea inside the ear, a neuron connected to a place that responds to 1 kilohertz, another one that connects to a place that's about maybe 1.5 kilohertz. And you look at how those two neurons are firing relative to each other. And then when you consider that information, he was actually able to account for a lot of the loudness data that's out there. So if anybody's familiar with like Weber's law, that kind of stuff, how loudness grows as you increase intensity, he was able to match a lot of that data. Masking. So I think most of us are familiar with masking, but it's basically the idea that you can have one tone in the presence of another. You can only hear one of them. So if you have, say, a broadband noise and you have a tone, if the tone is soft enough, you can't hear it. But then you bring up the level of the tone just enough to where you can barely hear it. That would be what we call the masking threshold. Unfortunately, again, if you consider, this is another neural modeling study, which I've been working on a lot for the past couple of years, so you hear a lot of that. But the basic idea is that you'll have, if you have a broadband noise, you'll have a bunch of neurons responding to that noise, but then you hide a tone in that. If the tone is soft enough, then it's not going to increase the firing rate, but at that same level, you can actually hear the tone in the noise. So it's not just the firing rate of the neurons that is impacting things. So when they included information about the timing, they found that that could actually explain a lot of the masking. And so the idea here is what they called a phase opponency model. So say if you have a tone, let's just say there's a spike at 1 kilohertz here, and then within the ear you have these overlapping auditory filters. And then if you consider the output of these filters, they're going to be slightly out of phase from each other. And so what they think is going on is that the brain is actually decoding the relative phase information across these two frequency channels, and that's how you're able to detect that tone buried in the noise. Here's a fun video. I'll just show this real quick. The idea here is that you use timing information for localization, the same inaural time differences that I measured before, and here's how people think that the brain is using some of that information. So this is an old model from 1948, and then I'll mention some interesting updated information based on this. See if we can play this. So there's going to be a wavefront, a sound wavefront, coming soon. If it will play. Okay, we'll explain what's going on. So let's say you have these two ears. So these are cochleae on either side of the head, and then they're sending neural inputs into the brainstem. So let's say you have a sound coming from the left side. It will reach the left ear first. Then you'll see this little ball that's shown here. You'll see a little ball of energy traveling down this neuron until it reaches this neural complex here. And then eventually the sound will also reach the right ear, and then you'll also see the neural signal travel to the brainstem in this area. And then you'll see that it takes a little bit longer for the sound to reach from the left ear than the right ear, because in this case the neuron is longer, so it just takes longer to travel down there. And then the signal will actually meet up at some specific place. And so the idea is that wherever the signal reaches a neuron at the same time, that neuron indicates what direction that sound is coming from. Yeah, it'd be better if I had the video. But let's just say that that was the basic idea from 1948 until about 2006. Philip Joris published a paper in which he showed, well, I guess there was evidence along the way suggesting that these neurons actually do not have different lengths. You cannot account for a lot of these delays by just looking at how long these neurons are in the brain. So the idea is that if you have, say, an interaural time difference of maybe half a millisecond, you would need half a millisecond worth of delay line inside the brainstem to make up for that. But when people actually did, surgeries and looked inside the brain, they didn't see that. They don't have these huge, long neural lines in there. So what he showed, what Joris showed in 2006 was that you don't have to have these super long delay lines inside the brainstem, because actually the output of the cochlea itself has delays. So what's actually going on is you're looking at the phase response of the signal, first of all, but then also the phase response of the signal going through the cochlea. So the cochlea is filtering the signal in some way, and it's adding its own delays. First of all, the biggest delay is, so you have sounds going in at the front of the cochlea, and then traveling down several centimeters worth of the cochlea. So by the time it reaches the end, you get low frequencies that are very delayed relative to the high frequencies. But then also, say you have, let's say, just a single tone, and it's soft enough that your ear is very sharply tuned to that. You get a very sharply tuned filter, you're going to get a lot of phase delay associated with that sharply tuned filter. So you see that that delay is also impacted by the signal itself, by the level of the signal, and of course the frequency, how sharply tuned the cochlea is to that frequency. And then, of course, also the health of the cochlea. So that's another thing that comes into consideration with some of these is as people lose their hearing, a lot of these things change, and so that becomes important there as well. So, moral of the story is that a lot of these delays are probably actually coming from the ear itself. So the ear is actually changing the phase of the signal. Another really important aspect is pitch. So this was a study done in 2010. Basically what this plot is showing you is kind of a spectrogram, but of neural signals. So this is what we call a neurogram. So the white parts here show where the firing rate of the neurons is high. The black shows where there's no firing. The bottom shows low frequencies, the top shows high frequencies, and then along the horizontal axis is time. So you see these patterns. It's basically just, as I said, a spectrogram, but in the neural domain. And what they argue here is that the ear is kind of doing a spatial derivative, if you will. So there's this line drawn. See if I can use the mouse cursor. There's a line drawn in this trough right here, where you kind of see this steep slope, and then it shallows out, steep slope, shallows out, and so on. And so what they do is they calculate this derivative, basically looking at what the slope is, and they come up with this dashed line here as a function of frequency. So this is the mean absolute standard or spatial derivative, I believe. But basically what you're seeing is these peaks across frequency. And so the idea there is that tells you something about the pitch of the sound by looking at where these spectral peaks are. And it's not calculated based on the energy in these different frequencies, but actually the slope of the phase, if you will. So the slope of this timing information. And then also this guy Eric Larson published a paper looking at if you have multiple pitches going on at the same time. He found that a lot of this rate information, so how fast these neurons are firing, so is useful if you have, say, a fundamental frequency above about 900 hertz, where the frequencies are very far apart, so you can get decent spectral resolution. But if you go to fundamental frequencies less than 900 hertz, so where each harmonic is more closely spaced, you don't get a whole lot of spectral resolution in the ear. So that's where this timing information is much more accurate. So for pretty much any pitch below about 900 hertz, it seems like this spatiotemporal derivative, or essentially what's looking at the phase information, is much more important for encoding pitch. And then there's been a few studies specifically on speech, starting with Shiab Sharma in 1985. He showed that, well, he didn't necessarily show anything. He speculated. He had a couple papers showing that there were these rapid phase shifts in the response, and that those might actually be really important for speech perception. And then Michael Hines showed that those phase shifts could actually let you encode speech that's buried in noise. So if you have a really bad signal-to-noise ratio, there's still these rapid phase shifts in the information, and those cues could be used to better understand what is being said. And then, I guess last month, showed that there's a lot of cochlear nonlinearities, of course. The ear does its own compression, and when it does that, it changes the phase response of the signal that's actually being sent to the brain. And so I specifically looked at how that affects vowels. And so if you look at the second formant of the vowel, which is really important for identifying what vowel is being said, that there's a lot of delay. I found, I think, 2 milliseconds on average of delay that was being added inside the cochlea. So there's a lot of phase shift going on before the information is being sent to the brain. And I also found that if you, let's just say if you look at hearing impairment, then that phase shift pretty much disappears completely, and so you don't see that there. So what we think is going on is there are actually neurons in the brainstem that are decoding a lot of this information. And there was a paper published about a year ago showing that these neurons in the brainstem, what's called the cochlear nucleus. So you have the cochlea connects via the auditory nerve into the brainstem, and the first, I guess, nucleus in the brain is called the cochlear nucleus. And they found that there are neurons in the cochlear nucleus that are actually sensitive to these phase changes. So what they did is they just simply played a click that had a different amount of phase. So you can think of it as just the impulse response of 2 different all-pass filters. So the click had a slightly different phase, if you will. And these neurons would fire differently depending on which of those clicks you played. And decoding some of that information is a bit beyond us at this point. It didn't necessarily just change how fast that neuron was firing or when that neuron fired. They had to build a complex statistical model to figure that out. But it seems like that information is being detected in some way, and then just it's up to several other areas in the brain to decode that information once it is detected. But so that's kind of where things are headed now in terms of trying to figure out what's going on in the brain in terms of detecting phase. So I thought I'd throw in a few quotes. I'm going a little faster than I expected here. But I found this paper published a few months ago where they cited a couple German papers, and I didn't have access to translations of these, so I just figured I'd use this quote. But the idea that the ear is phase deaf goes back to Ohm in 1843, and then Helmholtz kind of came to the same conclusion about 20 years later, that the ear is phase deaf. And I think we've seen a bit of evidence to show that it's not necessarily the case. And then you have quotes like this from Floyd Toole. I'll just read this real quick. He says, "The time domain behavior is not a serious factor, as humans are very insensitive to the phase shift, and only very large group delays, so larger than what would actually occur in normal loudspeaker designs, are audible. And even then, normal listening room acoustics make the differences even more difficult to hear." And that's very true. I don't disagree with him in any way whatsoever. But notice he's also talking about loudspeaker design, first of all. So I think the importance of phase really depends on what aspect of the audio system you're thinking about. If you're thinking about the actual original signal, or recording the signal, or processing the signal, or reproducing it, and then the environment in which you reproduce it, it all affects the phase in some way. So, if I'm going to be playing a signal over loudspeakers in a reverberant room, that reverberant room is going to really distort the phase, way more than anything that came before it. If you're listening through a nice pair of headphones and quiet, then you're much more likely to be able to hear a lot of these minute phase differences. So it really depends on your point of view. And then this paper, published by Stanley Lipschitz and his colleagues, where they're looking at phase distortion about the middle area of the audio spectrum. So he found that these phase nonlinearities that he was looking at were audible, that it was more audible on headphones than loudspeakers, as we just said. And that simple acoustic signals, it was easier to hear when there wasn't a whole lot going on. And then also he pointed out that with normal music or normal speech, it was much more difficult to hear these than it was, say, just sine tones or clicks or any of those. But he did find that there were a few recordings of vocal material where pretty much everybody could hear the phase differences. So it can come out in some situations. So a few conclusions here. So number one, we saw that phase can be very important. I mean, even if you think back to some of the demos of a flange or a phaser, phase is very important for those types of effects. But even simple things like pitch or loudness or masking, any of those, it can affect in small ways. The phase itself can be audible. A lot of times you're hearing kind of the effects of phase, the interaction of different frequency components beating with each other or modulating in frequency. So a lot of the very fine details you have to listen to very carefully to hear. And something I didn't really get into, but I think this is kind of a little bit more conjecture, but when you think about things like pitch, when you think about things like masking, those are particularly important things when you're listening in a cocktail party type of situation. You have a bunch of people talking all at once, it's very hard to hear what's going on. You have to really focus on what you're trying to listen to. So their very small differences can make a difference in what you're hearing. So I think phase is particularly important in those types of situations. And if you mess up the phase, I think a little bit more work needs to be done, but to actually show this conclusively. But my hypothesis is that phase is really important in those kinds of situations. So I've got a whole bunch of references if anybody's curious about those. But yeah, I figured we could open it up for discussion. Hopefully we can talk about some fun stuff. Yeah?
Regarding your last conclusion and a comment you made earlier about speech and noise, could you perhaps make this a little more intuitive as to what you're talking about? I'm familiar with speech understanding and noise tests and so forth, but usually when you talk about phase, there's some reference. So my view of a cocktail party effect is there's somebody speaking that you want to listen to, and there's a whole bunch of people that you do not.
Right.
Where does the phase reference and changes come about?
Okay, so just to get it through the microphone, as I understand the question was, how does phase become important in a cocktail party type of situation where you don't really have a reference? So yeah, a lot of these experiments have said, compare A to B, and can you hear the difference? But in a cocktail party situation, you obviously don't know what A is, you're just listening to B. But what you do have is, say, person A, person B, person C. And one of the biggest things, one of the biggest cues that people use to segregate sounds in a cocktail party type of situation is different pitch of people's voices. For example, where we saw that the phase of the cochlea can affect things. So one of my thoughts there is that if you have, the hearing of, a 16-year-old, you're going to have these very sharply tuned auditory filters, and you're going to get really good phase encoding in your auditory system. So you're going to be much better at hearing in a cocktail party type situation. Whereas if you get to be in your, say, your 80s and your auditory filters are much broader, you're not going to get that type of temporal coding in the auditory system. So I think that's one of the biggest problems as people age. Not only are you kind of smearing across frequency, but you're also smearing across time as well. So I think that makes things a bit harder to segregate. But then there's also the idea that in order to segregate different sounds, you have people will pronounce things at different times, and you can use that timing information to kind of piece together what one person is saying versus what everybody else in the room is saying. So even if you think about, say, the plosives in somebody's speech, you can kind of well. The idea there is that you could possibly piece together a lot of that information. And so that timing information of one person relative to another can be kind of thought of as a phase difference among people. Does that kind of answer your question?
Yeah, somewhat. Maybe you could turn this into an engineering type observation saying, with this knowledge, could you do anything to improve electronically or acoustically speech understanding?
Yeah, so last year I tried doing this. So I tried writing a DSP algorithm that would fix the phase. And the idea would be to make it easy for everybody to listen in a cocktail party type of situation. And the goal was, say if you have you wear these little things in your ears, let's just call them hearing aids, even if you have normal hearing. And the idea was that it would add in additional delay at different frequencies, and that should help you segregate out sounds. So what I did is I implemented this algorithm, and then I put together a computer model to see, what the neural system, how the neural system would respond, and I could definitely see that the neural spikes were happening further apart in time, as I intended. But if you calculate the relative phase at one frequency relative to another, which is what we think the brain is actually doing, that didn't change at all. So it seemed like really you can affect the signal going into the ear, but then the ear is going to be doing its own kind of decomposition of these signals. And so there was kind of a fundamental limitation that didn't work at all. So I think that idea has gone down the toilet, but maybe we can think of some new ones.
I'm trying to remember if it was researcher who suggested if you had like subwoofers on opposite walls and you put one 90 degrees out compared to the other one, that it gave you this nice sense of envelopment.
Sure.
Have you done this?
I have not done this. So the idea is if you have two speakers on opposite sides of the room that are, I think, 90 degrees out of phase from each other, was that the idea? That you get more of an enveloping sound. And I know that if you think about people's ability to localize, there's basic cues like you have the interval level difference and the time difference. And then you also have, some spectral details. But then if you also think about how well people are able to pinpoint where a sound is coming from, if you look at how similar the two signals are at the two ears, so essentially the coherence between the signal at the two ears, the more coherence you have, the more somebody is able to pinpoint where the sound is. So if you, I think the basic idea there is to decrease the coherence between the signals arriving at the two ears, and then it should give you a more enveloping sound. But of course the reverberation comes into play there as well, and so that complicates things a little bit. But I think that's the general idea. Sure, yeah. Yeah.
So as far as the cocktail party effect, something I've heard before recommended to people who have trouble that to say that phase almost operates like a frequency curve, where at lower levels we're able to understand the phase relation better, and at higher levels it smooths out?
Yes, I agree with that. In case anybody didn't hear it, the basic idea is if you have trouble listening in a cocktail party, put in earplugs. That lowers the level, but it also improves your ear's ability to segregate sounds. You get sharper auditory filters, you get better phase response. So it's, I think the main part is that you get better spectral, you get less spectral smearing, if you will, so you get better spectral resolution. But phase may come in as part of that as well. I don't know if anybody's ever actually done that experiment to show that earplugs actually help in a cocktail party, but that would be interesting to see. Dan.
John, when I think of phase, I think of the signal phase, and then I think of its first derivative, which is like the time.
Right.
In the sense the change in timing versus frequency or changes across the as a member. As far as I understand, there's no perceptual, we can't perceive the first phase changes. Everything is accounted for by the first derivative, that is the timing changes, and also the new evidence being this phase curvature, the second derivative.
Yep.
And I think everything you showed tonight would say the same thing, that when you say psychoacoustics of phase, it's really the first derivative of the phase. It should be the psychoacoustics of the first derivative of phase.
Agreed. Yeah, it's really the slope that matters.
Yeah.
Yep.
Yeah, so
the slope and the curvature.
So you have like in engineering terms, you have like a minimum phase system with some extra phase that you took out the bulk delay. That extra phase is not perceptible. It's just the timing differences that our brain is keying on.
I agree. Yep. Yeah.
What would you say to a naive audiophile that tells you, well, phase is important in my high fidelity system, and I can hear phase and all this stuff. It's something that gets thrown around.
Sure.
But I'm not aware of any, other than some of these home filter effects or interference effects, but just in changing wiring and things of this nature, anything dealing with phase that is said to be audible.
Right.
Do you have any comment on that?
My general response is to do a double-blind study. Without knowing the exact parameters, it's hard to say, whether the person is just hearing things or if they're actually hearing things. Somebody told me earlier today that they did an actual blind listening test where they switched the polarity of a signal. And I'm sure a few people in the room here know about this because it was done here. But you just switch the polarity of the signal and people could definitely detect the difference. And that's normally something that people think is inaudible, but they actually heard it as a sort of a frequency modulation. Anybody here know how that test was done? Was that over headphones?
I can give you an
Okay.
anecdotal observation. Years ago when I worked here, if you were developing a microphone and wanting to listen to it, and you were talking and you had earphones on, the polarity of the earphones would affect what you heard because your the occlusion components are a one phase to you.
Yeah.
And what you're hearing through the earphones are depending upon that polarity. So you could hear differences in the low end of your own voice.
Yeah, definitely, just because of the cancellation of the two paths.
Somebody standing next to you was listening, sounded the same.
Right.
So that you could say was an interference type experiment where polarity or phase were issues. But it wasn't that you just could tell the flip signal.
Right. Yeah, and a lot of times those fine little details kind of get left out, and so what might have been, you know, somebody says, oh yeah, I definitely heard the phase. Maybe they heard the phase of one signal kind of interacting with the phase of another, so they could, you know, hear some sort of modulation or cancellation going on. Yeah, that happens a lot.
So when you were covering phase delay and group delay, you showed how you could take a filter that was meant to alter the amplitude of different frequencies, and in the time domain it kind of smears where those frequencies show up. And so that was nicely plotted on the phase delay and group delay plots versus frequency. Is there a way of looking at plots for maybe the filters and designing and saying, wow, this group delay of X amount is going to be perceptible or not? At what point does it become noticeable?
Yeah, I mean, it's kind of hard to give a blanket rule of how audible it's going to be. It's probably going to be dependent on a lot of factors, you know, what you're listening to it through, maybe even what frequencies you're looking at. There have been several studies on just trying to figure out, you know, how much group delay you have to be audible, and, you know, people have thrown around the value of 2 milliseconds, but again, that's very dependent on a lot of the situations, the specific variables that are going on. So it's kind of hard to say how audible something is going to be without listening. John?
Going back to the bass guitar experiment stuff that we did, what made sense to me was that when you flip the polarity, you get a timbral change. It's easy to hear in an A/B test. What made sense to me was that there was some nonlinearity happening either in the driver or in the ear that's causing either different time shifts or different amplitude shifts in harmonics.
Yeah, and so there's a whole lot of nonlinears going on in the ear. And so for that particular case, the way that Bob explained it to me was that if you look at the actual signal, it wasn't exactly symmetric, you know, positive versus negative. And if it was symmetric, then it'd probably sound pretty similar. But because it wasn't symmetric, and because your ear is actually doing a half-wave rectification, it's only looking at one side or the other after it passes through some filtering, there will probably be a big difference if the signal is very asymmetric. Yeah, exactly. Yeah.
The conclusion from that you're saying is if it were like a pure sine wave or something, it wouldn't matter what the phase was. So they were testing a complex.
Yeah, that was a bass guitar, I think you said. Yeah. So yeah, a sine wave, one single sine wave, the polarity of that, if there is actually no distortion, no amount of reverb or anything like that, then you're probably not going to be able to hear that. Right. Yeah.
The studies you mentioned before about audibility of group delay, or what is the J&D of group delay, were they considering constant group delay, or were they considering a peak group delay when I'd seen them?
Right, and so that really depends. And as Dan was pointing out, it's really the derivative, you know, so what is the slope of the phase, what is the exact curvature of the phase, that's going to make a huge difference in how audible it's going to be. And so I think I've seen a couple different ways of doing that, but definitely, I mean, the more narrow of a group delay function that you see, the more audible that's going to be. Anybody else? Oh, more.
Going back to the cocktail party, one experiment that was done, they're looking at cochlear implants, and notice that people don't get any release from masking as you would people talkers for their party.
Yep.
And the same thing happens with vocoding. You remove all the phase information if you vocoder the signal. And then you can't discriminate direction and
yeah, a lot of this, what a lot of the cochlear implant community calls temporal fine structure is very important for a lot of the localization cues. And yeah, cochlear implants are really bad at that. Mm-hmm.
A lot of things come to mind, in my mind at least, about music appreciation. For instance, vibrato versus tremolo. And then I think of if you have sometimes a very accurate male chorus, you could hear soprano tones that are mixed somehow and appear, you hear live. But thing at group delay, a lot of people who run sound will add vibrato. Delay, and sometimes it's so objectionable. When I listen to that, a little bit can be very attractive, but just a little bit too much. It's like, what are they doing?
Yeah.
You know? And I think this group delay gets distorted.
Yeah, and actually, we did a study here at Shure several years ago where we looked at how much delay is too much delay when you're doing a live sound monitoring type of situation, and just doing linear delay. We found that it definitely depended on, say what instrument you're playing. People who played, vocalists and a saxophone player we had were very sensitive to these very small time differences because they were getting the signal from their own voice or from the instrument directly through maybe even some bone conduction into their ear, as well as the delayed version that was being amplified through whatever sound reproduction system, and that was really bothersome to some of those people. John?
On that, I have spent some time on sheer boredom experimenting with using time delay in live sound playback to create stereo images rather than panning.
Mm-hmm.
Panning in a large room with everybody spread around does a disservice to a lot of most of the people in the room. But small amounts of time delay can give people a sweet spot, a nice stereo image without wrecking the mix. It does work really well. It tends to become gear intensive.
Yeah.
Maybe like doubling up channels and delay, like have guitar one, delay a little bit.
Yeah, like using two short delays and busting out to a stereo delay.
Yeah, I actually tried implementing once a temporal panner instead of just panning the intensity, actually pan the time. And the idea was that you could create a larger sweet spot, ideally. I had a little trouble getting it to work without, because if things move, then you hear some of these like phaser type of effects. So that was a problem.
No, it works really well. And with digital consoles now, you should be able to do it. It's just nobody's implementing these things.
Cool.
So, we're going to digital console manufacturers.
One more, Bob.
Now, you mentioned at one point that folks with hearing loss have much harder time instrumenting phase.
Yup.
So, would that explain why folks who wear hearing aids in a cocktail party is even worse? Because the hearing aid raises the intensity, but it ends up sounding more like noise. It's very hard to discriminate a single person in a cocktail party, even though you've got amplification.
Yeah, there's a rather well-known study where the title of the paper is Hearing Aids Without is Better Than With. And they showed basically in the cocktail party type of situation where you're trying to segregate out a bunch of different signals that are occurring in different spatial locations, but at the same time. Yeah, the hearing aid just really mangled things up bad. And so, yeah, there's several things going on there. The hearing aid is adding its own delay. The delay on one side relative to another may not be perfectly aligned. The level on one side versus the other may not be perfectly aligned. Overall, it's making everything louder, kind of smearing everything together. So there's a lot of work to be done.
All right.
All right.
Well,
Thanks.
maybe we're formally over, but not completely.
sure there's room for more questions just directly. And are you up for going next door?
Sure.
All right, all right. So it'll continue, and we'll loosen up and be more free to ask our real questions. But thank you so much. Here is your official plaque.
Sweet.
And the mug. And the last of our mugs, by the way. Yeah, we're going to go over here for the picture. Don't worry. I'm just doing this just to mess with Bob.
I'm kidding.
That was fun. All right, so the official photo. I'm so tired of seeing myself. For HQ. So thank you so much. And thank you, by the way, I meant to mention thank you to Shure for having us, especially those whose arms are twisted to stay, whether they want to or not. But thanks, everybody. We'll wrap up. And